Yes, good. Okay. Thanks, Andre. Good morning to everyone and welcome again to another webinar session from my side. And today we will be doing a session on RelaySimTest, and our webinar or presentation and demonstration will be on the testing of a simple buzzer scheme, which is configured with GOOSE using the RelaySimTest. So before I start, I would also just want a quick shout out and thanks to the SEL guys. Thank you guys for the support on your side and also borrowing us the relay that we are using for this demonstration. Also thanks to Theo and Pietri for loaning us the CMCs for the setup and testing of this configuration. So just want to shout out to the guys, say thanks for the support, we really appreciate it. Moving on then from there, we can now look at what our agenda for the day will be. So our agenda is obviously to look at what is RelaySimTest for the guys who have not been introduced to it and hasn't seen it yet. We'll be looking at the benefits of RelaySimTest. We'll be looking at where to apply RelaySimTest. And then we will look at RelaySimTest and IEC 61850, which is something which is very relevant for today. Then we will be moving on to the practical demonstration. And in our practical demonstration, we'll obviously be testing a simple buzzer configuration, which is configured with GOOSE. And I will give you guys some details and explanation on the single line diagram for the configuration. I'll show you what the physical setup looks like. And then we will start looking at how you go about configuring and testing the system. So just as we start with what is RelaySimTest, for the presentation side, the theory side of it, I'm going to be scaling down on the information quite a bit in the interest of time. We will also be sharing the brochure for RelaySimTest with the email that Andre will be sending out after the webinar. So if you guys are interested, you can always read more up on that and look into that, or alternatively, just reach out to us, contact us, and we can get to you guys and give you more information. So what is RelaySimTest? It's a revolutionary testing solution which introduces system-based testing in addition to the complement the already very well-known and applied parameter-based testing. So it's more seen as an addition and a complement to test universe and should not be seen as a substitute. So many people will always also often reference RelaySimTest as the poor man's real-time digital simulation or the poor man's commissioning tool. And this is because it allows you to do system parameters and configurations, and then you can test these systems. So it's a system-based testing approach, and it's independent from the relay type, the manufacturer, and the detailed parameters. And it can be used to evaluate complex and adaptive relay logic and algorithms within the system. So what are your benefits? Once you get started and have worked with RelaySimTest, the benefits tend to become more and more. And here we can highlight just a few, and we can look at what we've listed here on our slide. So RelaySimTest is a complementary testing solution with Test Universe and should not be considered as a substitute, as I've mentioned earlier, and it should be seen as an extension of it. It allows for easy testing, which is independent of the complexity of the protection. It is capable of testing adaptive relay logic and algorithms for complex protection functions. When used with Test Universe, as I've mentioned, it's seen as a complementary to that. In addition to it, it will improve the overall quality of testing. It also allows for automated test reports, whether it be one or multiple CMCs that you are running on your system. The report is generated into one single document. And then ultimately, all of this would result in the reducing of testing times. Okay, so where to apply RelaySimTest? If we look at what I have there, the first one is for transient simulations. So to ensure your protection system is working as expected, RelaySimTest can calculate its test signals via a transient power system simulation. This enables the users to investigate their protection system under challenging conditions like CT saturation, power swings, weak in-feed conditions, in-rushes, and many other conditions. As the test signals are like real-world system events, even adaptive or time-domain protection functions can be tested, which we've already introduced to the guys at our user conference in 2019, something like the traveling wave protection functions, which SEL also have launched the SEL T400 relay for. Then we also have our control of multiple CMCs. So with RelaySimTest, you can control all connected CMCs, whether it be one or multiples, from one PC with a simple network or internet connection. You can execute distributed tests across substations as easily as a single relay test, regardless of how many CMC test sets are being used. This has the following benefits: no phone coordination, so you don't need to phone the guy on the other side. If you have RelaySimTest and you are connected to the other CMCs, you can run it all from one PC. Multiple test steps can be executed automatically. The automated assessment involves the response of each end relay and gives an immediate response if the test has passed or failed. It also has the benefit of the on-site changes in the test document that is possible. So if troubleshooting is required, you can easily adapt it to that. And then a single test report summarizes all the results into one document. In addition to that, it also has a function which is called the iterative closed loop for testing logic. I can spend hours on explaining how this works. We are making use of this function, but with the patented iterative closed loop method, RelaySimTest can automatically adjust test signals according to the trip and close commands. This way, testing an auto reclose function becomes simple and transparent. And for today, we are using this exact iterative closed loop logic in our bus zone protection scheme to prove the operation of the bus section in terms of the coupler security logic that's been applied. Adding furthermore to the previous slide, to have a more lower level look at where RelaySimTest can be applied, it can be applied into a wide range of various protection applications, such as the busbar protection, for example, for today, break and a half scheme, auto reclosing application, traveling wave systems, and so much more. We will send the brochure, as I've mentioned earlier, at the end of the session today, so you can have a look up at more of these applications and read up on that in the brochure in detail, what it's covered and what it is entailing of. Okay, coming now to our next slide, RelaySimTest and IEC 61850. Now, leaning a bit more into our presentation for today or our practical session, the full IEC 61850 support in RelaySimTest allows the users to import the substation architecture or configuration. So this would be your typical ACL or ACD or your ICD, CID configuration files and so on into the RelaySimTest so that it becomes part of your test system. So this feature then allows you, amongst others, to simulate the GOOSE messages, which is something we'll be demonstrating quite a lot today. The simulation of sampled values, and it will also support the connect to multiple virtual or physical networks, in other words, your VLANs and so on, and add extra security by running automatic validation processes. In context to our exercise today, we are using the GOOSE simulation capability to simulate all of our virtual inputs to our relay, while also at the same time test the logic and algorithms associated to these test signals. And that actually brings us then to what our practical demonstration will be like today. So my practical demonstration today, I have my two CMC 356s, each giving me 6 current output channels, which I'm using. I'm using one CMC 430 with 3 current outputs. And then obviously I have my ACL 487B relay, which is consisting of the 21 current inputs. And then I have one PTP transparent switch that I'm using to connect this whole system into a network. Giving you guys an idea of what the single line diagram looks like. So as we've mentioned, this is a very simple bus zone scheme that we are running. So my simple bus zone scheme is a single bus bar or split with to 2 bus bars with a section in the middle. In other words, not a double bus with a parallel bus, it's a single bus with a section in the middle. Then I have 4 bays. In these 4 bays, I have incomer 1, I have incomer 2, I have feeder 1 and feeder 2. Now, typically a system like this could also be configured with 2 CTs over your bus section. This example for today, I've gone with a single CT, and that's simply because I was planning on using 2 CMC 430s, and then at the last minute, I decided to go with only the 1 CMC 430 because that also allows me then to demonstrate the coupler security logic of the ACL relay. So I've eliminated this for the time being, but it can easily be implemented, and then you can add another CMC to inject on this. So the way I've set up my system now is I'm injecting with one CMC356 the two incomer CTs, 3 phases. So 1356 has got 3 channels here and 3 channels over here. And then I have a second CMC356 injecting on the current channels over here and over here on the feeders. And then on the bus section, my CMC430 is injecting on the CT over here. Then in my relay logic, I have taken all these current CT inputs into the relay. They've been wired to the relay and they've also been used in the logic, as well as these statuses for the disconnectors, as well as the breakers, and then also for the disconnector, the 2 isolators or disconnectors, as well as the breaker. In my logic, I've also defined the coupler security to then negate this CT so that this CT is looking at this side of the bus bar as bus bar 1, and it's looking at this side of the bus bar as bus bar 2. So all of this is done internally to the relay logic, and at the end of the day, we would just need to test this system by simulating fault conditions in zone 1, zone 2, and then obviously that's a very tricky one in this dead zone that we have over here between the breaker and the CT. We will also be simulating that for our exercise today. So it's also important to mention that a lot of times when you consider the coupler security logic, there's 2 things you need to consider on the buzz-in side. So in the one application, you can prioritize speed above selectivity. And if that's the case, you would not use the coupler security the way I've done today. This is typically the configuration that is used for HV schemes. I've gone for the prioritizing the selectivity instead of the speed, which means if I have a fault over here, I'm not tripping out the zones as fast as I can, but I'm tripping out the section on an accelerated trip, and then I'm re-evaluating my system to take out the zone 2 instead of the zone 1. Why is this a problem with a single CT? Well, simply if you consider the setup that we have here, if I have a fault on this side, it's obviously a zone 1 fault. And if I have a fault here, it's a zone 2 fault. The problem comes in when I have a fault between the breaker and the CT. And this is a challenge now because I'm using a single CT, so I can't cross-reference this, which means if this breaker opens and the fault was here, I would still be feeding that fault from zone 1. And in that case, if the fault was here, zone 2 would have immediately tripped. And if the fault was still there, obviously it would have been because the breaker is now open, I'm still supplying a fault here, then I would still have this feeding that fault, and then I would trip zone 1. And that's if you select speed as a priority. What I've done here today is I've selected selectivity, which means if I see a fault here, I accelerate trip the section. The section then opens, removing all CTs from the equation. And then with the fault being here, it reassesses the buzz zone, and then it accurately trips out only zone 1. And we'll demonstrate this in our testing a little bit later on. Then giving you guys a bit of a look at what the setup looks like here in front of me today. As I've mentioned over here, my CMC 430, and then my 2 CMC 356s, the 487B relay, as well as my laptop, my engineering laptop or testing laptop running RelaySimTest. And at the bottom here, this is our relay at the back. I'm highlighting it here so you guys can see that there is no physical connections on any of the inputs or outputs. Everything is simulated on GOOSE. Okay, so why are we doing this today? So the concept behind this is to show you guys how RelaySimTest can support you in testing not just a simple buzz-in scheme, but also like something like an 18-bay buzz-in scheme, where yes, you would have hardwired tripping signals and you would have hardwired inputs, but if you in parallel add logic to the relay for testing purposes, and this logic is a virtual logic, which is GOOSE. If you're making use of that GOOSE in parallel, you can then switch between the hardwire logic and the GOOSE logic, and thereby then test the full buzz-in system without having to wire all of these inputs and outputs just to test. I mean, considering testing an 18-bay buzz-in, if you have to wire in, and let's say, for example, it's a double bus with a transfer, then you have so much wiring that you would need to do to get all the breaker and isolated positions into this relay and simulate all of that if you want to do a full system functionality test. Now, what RelaySimTest allows you to do then is if you have that GOOSE configuration as a test logic in the background or in parallel, then you can easily just move on from that and switch to that and test by simulating with RelaySimTest these GOOSE messages being published to the relay and the relay subscribing and switching automatically. So this can be done in a couple of ways. You can obviously also make use of IEC 61850 edition 2's test mode, which is not used as often as what it should be. For today, what I've done is I've made use of a much more simpler application, and I will quickly show that application just now as we start getting into the practical side. So that's it from my side in terms of the presentation, the theory. So I think we can end this now and then maybe go on to the more fun side of things, which is going to be to actually then test the whole system. So I'm just quickly going to do the screen share swap. Just give me a second there. We can. Okay, so I trust everybody can see my screen here with my Lego set at the background. Andre, can you maybe just confirm for me that, please?
Yeah, I can see the Lego background.
Perfect. So what I wanted to show you guys is this. So this is the much more simplified approach that I took today in terms of what I'm simulating. So obviously for your isolated closed position, you can have your hardwired input in 101. And this can be conditioned then to say when the virtual logic is enabled or disabled. And if it's enabled, it's knotted. So if it's enabled, it will disable this control logic here. So it will not be using this together. So if you have virtual logic enabled, the negated function here will completely block the hardwired signals going into this status. Whereas if I have now the virtual logic enabled, this should actually be negated here as well. My bad. I quickly drew this up this morning just to give you guys an illustration. But what I would have here is in the virtual signal and the quality signal, as well as that enabled signal here. That description is not right. But then I would have this logic enabled and that disabled. And when I switch back to the hardwire signal, I would just simply disable the virtual logic, and then I would be completely and solely relying on the hardwire signals coming into the relay. So obviously it's important during commissioning and FAT that the hardwire signals are proven. Typically during a FAT, these hardwired inputs will be tested one by one. So the argument would stand that they would be existing and be tested. So when you want to implement a virtual logic in the background or in parallel, this can also then be tested using your functions. So this would be then the output going to the relay. In my case, this is ASV001. And this is now the part that I'm going to move to my relay quickly and just quickly show you guys what my relay configuration looks like. Okay, so let's bring up the relay. So on the relay side, if I can show you guys here on my disconnect to inputs. So these are the signals that's being used. It's the ASVs. So I've used these ASVs, and in the logic, if I just go down to my automation logic to give you guys an idea, if I look at ASV001, which is my income 1 close status, this is where I will be getting that signal. And this is where that signal is working with the logic. So this is the part that would enable the logic for hardwire, and this is the part of the logic that will enable it for the virtual signals, which is the GOOSE messages that I'm using today. So once you have configured then all these disconnector inputs to the respective positions on your relay, you can use these disconnectors in your terminal switching logic. So then I'm using that 89 CL01 to switch in my CTs into the respective bays. Now, I'm not going to spend a whole lot of time of explaining and detailing the logic here. I just wanted to make you guys aware that we are using two sets of logics here. The one is the hardwire one, which we are not using, and I'm showing that so you guys have the idea in the back of your mind that this is an application where you can have the hardwire logic still existing in the relay, but in parallel, if configured from the onset, you can have a virtual set of logics which test exactly the hardwire functions, but just virtually with the application of the GOOSE. So obviously, if you have configured the relay to use GOOSE, you would have to also then configure your relay to receive GOOSE messages. And this is now another part that I would quickly want to explain, because you would notice here on the left-hand side, I'm using two relays here. Obviously, the 487B is my boson protection relay. This is the relay that will be under test. And then you will notice this one here. And the reason why I'm explaining this is because this is relevant when we get to RelaySimTest. This is just a dummy relay. This is a simulated relay. It's not an existing relay. I don't have this relay present here today. It's not connected, but I'm only using this relay so that I can then send out signals that my 487B relay can subscribe to. So if I look at my 451, I can look at the GOOSE that's being transmitted here. I'm sending data set GPD01. So we can just maybe go to our data set here. It's this guy over here. So here is just all the signals that I've configured. So yes, for the guys who are familiar with 61850, I could have used the 61850 work bits for breakers and disconnectors. I could have done that and stick strictly to the 61850 standard, but I've gone for the GGIO simply because as a protection guy, I like to associate input 101 with virtual bit 001. So I can make that relation to say that my virtual signal, which is one signal, is replacing my input, which was another signal. Sure enough, you could have used the double bit statuses from the 61850, and you could have used that. I've just gone this route, which is one way of doing it, but I've tried to make it as relatable as possible for a protection guy looking at an input and having to consider that that input is now being substituted with a virtual signal. So now obviously my dummy relay has a data set which is being configured, and this data set will then be published onto this network, and then that is being published with this GOOSE transmit block that we have configured here. This is just to say that this is a data set with its data attributes that will go onto the network. That means now this 487B relay can now subscribe to that relay signals being on the network, and that's why we also see that 451 relay here. So all that I've done now is I've taken these signals and I've just mapped them into my 487B relay so that the relay in the background can know when it receives a virtual bit 001, that signal is the signal that is being sent or published by the 451, and that would be the 451's PSV01. Okay, so for the guys who's not familiar with SEL, this might be a little bit unfamiliar, or you might not recognize it, but simply what I'm doing here is I'm telling my 487B relay when it receives a virtual bit signal, that virtual bit signal is being published or sent by my dummy relay, which is the 451, and the 451 is sending that signal from its configured PSV logic 1. That's straightforward what it means. It's just a virtual signal that's being sent to the 487B, but I need to tell the 487B where that signal needs to be allocated, and then in the logic, I need to tell that relay what to do with it. So obviously, I've used virtual bit 001 as the close status for incomer 1. So in this way, I've configured the relay to recognize it and know what to do with it. And in the architecture, I have configured it so that the relay knows when it sees these virtual signals, where to route it to and what to do with it. Okay. So now that we understand what our system looks like and we understand what our relay configuration and the 61850 configuration look like, what I would do next is export. I would just export this SCL or CID file. And once I've exported it, it will be exported into an SCL file, which would look something similar to this. This is now my RelaySimTest buzzer and SED file. That just means it's my substation configuration file that I've created. And that file is now the file that I would need to use in my buzzer relay, my buzzer scheme in RelaySimTest. Okay. So now that we've wrapped that up, I'm going to move over to RelaySimTest, and I'm hoping you guys are making notes and asking questions. So at the end of the session, we can look at all these questions. So going forward with RelaySimTest, I'm going to slow a little bit down because I want you guys to understand what we've done in RelaySimTest. So obviously you can launch RelaySimTest, or you could just open the test document over there. And once you have RelaySimTest, you'll have the landing page or the starting page that looks something like this. Now, obviously, this is not a training session on RelaySimTest. This is more towards showing you guys what RelaySimTest can do. So this is a very familiar screen. Most of Omicron software looks like this. You can go around and look at all these different options here. You have getting started. Over here, you have the getting started videos. So you can have a look at these videos. There's also a video on YouTube for that. And then sample documents, followed by Omicron news. On the left-hand side, these are all the recent test documents that I was working on. And then over here, you have the options of opening a new test document, opening an existing one, or you can open a device remote agent. Excuse me. So obviously, this is the landing page. You can just click here, and then it will start your RelaySimTest. So if I click on my last used, it will open up my last configured test plan for RelaySimTest. Okay. Now let's start having a look at what RelaySimTest offers me. So at first glance, what you'll see here is on the left-hand side, this is the view. This is your condensed view. We have all your high-level interactions. And on the right-hand side, this window over here, this window is where all the testing plans will be, where you would create your system and put in all the details. This is where the configuration side will take place. So on the overview, I have here an option to put in some details, add some comments in here, put in who tested it, who's executing these tests, and then it will also give me an overall assessment from my system, which you can see I've run this test actually this morning, and it passed. It was all green flags. I'm happy with that. And then obviously I can also generate a report by just saying export to Word, and then it generates that report for me. It can be customized with a logo, so you can put your own company logo in here. I put the Alectrix mascot in here. And then also you can customize the test report in the sense of what blocks out of this test you want to include or exclude. Now, the more important or most important part here is the system. So this is what RelaySimTest then allows you to do, is to configure your system under test. Okay, so the system under test for today is our buzzone scheme. So I've already gone through the exercise of configuring this. So this is what you guys are seeing here now. Just similar to my presentation earlier on, you would have seen that I've got my 4 bays here with my bus section in the middle and then my bus bar. I've split my bus bar here to a left-hand side and a right-hand side. And then I have for each bay, I've added the breaker, its CT, and its isolator or disconnector. And that is then duplicated for all the bays. Similarly to my section, I have over here then my disconnectors, over here the other disconnector, and then I have my breaker in the middle, and then the CT over here. What's important is that you have parameters that you can configure for the system. So if I just take a step back and quickly just clear my results, we can see what becomes available. So if I go back here now and I click, so now you can see that you can configure it by defining its unique name. You can set the voltage, you can set the phase angles, you can set the impedances, the positive and the zero sequence impedances, and the grounding application. You'll also notice that I have here just a description for the breaker, and I've set this breaker as incomer 1 breaker. It's a 3-pole breaker. And then I have my disconnector here that I've also just labeled incomer 1 isolator, which is the disconnector. And then this initial state is I can just simulate if I want to have this state initially as closed or open. Okay. The one that I want to spend a little bit more time on is the CT, because the CT, once you've added the CT, there's an option of a single phase or a 3-phase CT. So obviously my relay I've configured to see 3 phases per bay. And that means I just uniquely named them as per the terminal connections on the relay, IO1, IO2, IO3, continuing that sequence throughout the bays and also on the isolators of the CTs of the bisection. Then I have a couple of parameters that I can set here, CT ratio for the primary and the secondary, and then the one that I want to just quickly mention here is the toggle option. So obviously the toggle is, if you pay attention to this CT here, if I toggle that, it switches the polarity, and as per standard practice, my CT start point must be facing towards the object under protected object. So this is the protected object, in this case is my bus bar, so it's pointing towards my bus bar. You would recognize that this CT, however, does not point towards the left-hand side, but to the right-hand side. That is how the system is set up. The relay is also then set up to negate the CT onto the left-hand side and using the inverse current flow to balance out with the left-hand side. Okay, so that's basically looking at what our base configuration looks like and our bus bar configuration looks like and our bus section configuration looks like. You'll also notice here on the top, there's 3 icons here, which is the 487B, the SEL451, and my subnetwork 1. Okay, so if I'm going to click now on the 487B, and if you pay attention, you'll notice that suddenly it highlights a couple of blocks here with a pinkish purple hue, and that indication of these blocks being highlighted, that is just showing me that this 487B is associated or connected to all these devices that I'm seeing here. So obviously that means the 487B is getting all the current inputs from the respective bays and the section. It's also connected to the 451, and it's also on the same network as the subnetwork 1. If I now go and I click on subnetwork 1, you'll notice that subnetwork 1 is then consisting of my 487B1 and my SEL451. Now remember, this relay is here because this is a dummy relay. So how did these relays came to be here? So I simply imported the SEL file. That's that SEL or SED file that I showed you guys earlier under my relay configuration. It's this guy over here, okay? So I imported that configuration and it created this for me, showing me that I've got a 487B and a 451. I had to just associate the respective devices that's connected to the 451, and then similarly, I had to associate the devices that's connected to the 451 as well. So over here, we can see that all the breaker and disconnectors are associated or configured to the 451. And that is now where the 451 is playing its role to simulate these statuses for the disconnectors as well as the breakers, so the buzzer and relay, the 487B, can subscribe to that. Okay, so I've talked a lot about it's connected and it's associated to these devices. So let's have a look at what that looks like on the IED side. So if I double click here, or I could just click there on configure, it now opens my configuration screen. So in the configuration screen, at first glance, you'll see that these are the devices again that is connected. So typically it would be highlighted like this with a dashed line. So if I wanted to connect this, I would just click on that and then it becomes connected to the 451. Obviously that is not the case, so I don't want it to be like that, but that is how simple it is to associate or to configure certain aspects of my system to a specific relay. On the left, okay, so this is the system that I'm seeing. On the left-hand side, I'm just seeing a breakdown of what the functions are that I need to do. So the first step is the device connections. That's the associated functions or devices to the ID. And then I have my general settings. So I can put in here the IP address if I wanted to, but this relay being a dummy relay, it doesn't have a lot of functions to it. So there's not much that I need to add in general settings. Also, you would notice, and I'm going to mention this later on again, it's got a blue color on this left-hand side, which is an indication that this is a simulated ID and not a physical existing ID in the system. On the simulated binary outputs, you'll recognize there's nothing because I'm not using this relay or any of these relays with binary inputs or outputs. It's all based on 61850, which means I'm going to the next step, which is then 61850 setup. So obviously here I could import the SEL file again. I've already done so. So I don't need to import that again. So I can move on to the next step, which is now looking at the simulated GOOSE outputs. Now this is where earlier on when I showed you guys the architecture and the data set, that's over here. If I can quickly just recap back to that, show you guys here. If I go to the data set and I open that respective data set, you'll see this is where all those PSV signals are sitting. This is the data set that's being published with the data attributes. Coming back to RelaySimTest, these are now exactly those data attributes in that exact same data set. So my relay here knows this is a data set that it's being published. Now, obviously, when I'm saying my relay here, this is a simulated relay that knows this is what's being published. And over here, you can see that I've already configured this data set, that this is a Boolean output, which means it's just a binary input that's simulated to incomer 1's status. And so I've gone through all the different bays and I've associated all the different bases and all the disconnector and breaker positions I've already associated to these attributes over here. Why is this important? Well, we'll get to that part when we start with the testing, because at the testing stage, this is being used. And then the reason why I've linked these virtual signals to these descriptions on the right will make a lot more sense. At the same time, I can also say that this relay is subscribing to trip signals being received from my 487B. Now, I've not discussed the 487B just yet, but that relay is also publishing signals, and the signals that relay is publishing are my trip signals. So this would be trip for incomer 1, incomer 2, feeder 1, feeder 2, and then the bus section. Also, similarly, these have been connected to certain bays and their breakers. And this is, again, when I get to the testing part, I would need to know if I receive this signal, what is this signal, where does it come from, what is it used for? This is where I've defined where it comes from and what it's used for. Okay, obviously we're not using sampled values. So the first 3 steps are the important ones here for me to configure my simulated relay, which is not a real or existing relay. I can now go back to my power system, and now I want to have a look at my 487B. So here I can click on configure, or I could have just double clicked on the ID. And again, I have a similar screen. I have my power system here, again, highlighting what has already been connected to my 487B and what else I can associate to it. Okay, I don't want the statuses here to be to the 487B. I know that's going to the 451. I know this relay is only looking at the current terminals. Okay, on the left-hand side, you'll now recognize this is highlighted in a gray color scale here, and this is to just differentiate between what's a simulated relay and what is an actual relay in the system. I again have my general settings, which now would look a little bit different because this is not a simulated IED, this is an existing one. So I need to define this as a digital relay, set some parameter limits for the currents and the voltages and the device address and details. The next step is then the analog input. And this is where it's important when I mentioned in the system configuration that there's an option between a single phase CT or a 3-phase CT. So obviously I've included 3-phase CTs, and had I included a single phase CT in there, I would only have one terminal for that specific bay. But since I used the 3-phase CT, as you can see here, it shows that it's got a 3-phase CT here. I have the option of a line 1, line 2, line 3, and neutral. And I've just given them the unique names as they are associated to the relay terminals at the back. So this is IO1, IO2, IO3, going all the way through the sequence up to IO15. Now, had I used a system with a second CT on the bus section, I would have continued here with I16, I17, and I18, and I would also simulate that CT then. Not the case for today, but just worth mentioning. So these unique names, I've added these descriptions, I've added these names, I've given them to the CT, and I've done that because later on, when I need to differentiate, when I'm monitoring the transient system, what are the values that I'm seeing? I need to know, am I looking at the incomer, the feeder, or the bus section? And this is how I would know what currents I'm looking at when. Binary outputs, once again, I'm not using any binary outputs or inputs on this relay, so I can completely ignore that and go to the next step, which is the 61850 setup. On my 61850 setup, again, I can import the STL file. I've already done that, don't need to do that and break my system right now, so I'm going to leave it as such, but you would just say import and import that file that I mentioned earlier on. The next step is my GOOSE output. So this is where I'm saying what these signals are. We mentioned this on the 451 side as well, but these are the signals that's being published by the 487B relay in its data set to the network, and then my RelaySimTest will be subscribing to those signals as it's being published. Again, I need to tell RelaySimTest then what these signals are. So this being incomer 1, if I click here, you'll see it's incomer. This is supposed to be incomer 1. Okay, there we go. That's incomer 1, incomer 2, incomer 3, feeder 2, bus section. So again, I can give this a unique name. My Zoom icon thingy here is in the way. There we go. So incomer 1, 2, feeder 1, 2. So I have this now added twice here. I can just take that out. I don't need it twice. I've got it 1, 2, 3, 4, 5. Good. So to highlight what these signals are here, incomer 1 is the first signal, incomer 2 the second, feeder 1 the third, feeder 2 the fourth, and then the bus section the fifth. Again, I've given them unique names here so that later on I can identify them and then I can use them and recognize them. Okay, So in a nutshell, that is my system that's been configured. So from here, once my power system is set up, I've added all the parameters, I've linked and associated all the devices, I can now run almost unlimited amount of tests on this system to rigorously test the system and see what the system can do. Now, obviously, we are limited for time, and I don't want to keep you guys here for the whole day, so we'll be running only a certain amount of times of tests. Okay, let's now look at our test configuration. So for the guys who are familiar with Test Universe, you'll always recognize there's the hardware configuration. And the hardware configuration is where we are saying, these are the currents that's being used, these are the binary inputs and outputs that's being used. And in RelaySimTest, it's relatively similar, but not exactly the same. This is better. So let me show you guys what I mean with this is better. So if I go to my CMCs here, now I click on the first CMC, which is my Alectrix CMC 356, you'll recognize on the analog outputs, I have my 3 current outputs that is displayed over here. Also, in addition to this, it's showing me that current output A is being associated to incomer 1, and current output B is associated to incomer 2. So if I need to retest the system and I open up my hardware configuration, at first glance, immediately it tells me what am I connecting where. You also notice that these descriptions and names here are the unique names that I assigned when I went through the power system on my 487B side when I looked at the analog signals. So having those detailed signals available there makes it so much easier for you to uniquely identify and to retest if you need to reconnect the system. So for example, for me, I tested this system about 3 weeks ago. Coming in here yesterday and setting up the system again was just as easy as saying, okay, I know this goes to incomer 1, this goes to incomer 2. So the reference is there and it's easy to use. If I'm still on the same CMC, you'll notice no binary inputs, no binary outputs, and that is because I'm using the GOOSE. Going to the second CMC, now the second CMC you'll recognize current output A, current output B is both connected then to feeder 1 and feeder 2, again showing me the unique names to immediately I recognize and identify them where these signals need to go to. And then the last one is the CMC 430, and this is connected to my bisection single CT, so I have my current output here connected to my bisection over here. Okay, so this is what the hardware configuration looks like, and you'll see that the binary inputs and outputs for all of these CMCs are empty because I'm not using them at all. Okay, so going back to my full system here, before we move on, the network, you'll also recognize that from my power system, we remember there was a subnetwork 1. If I can quickly show you guys back here, this is subnetwork 1. I know 487B and 451 is on subnetwork 1. And if I go to my network here, I can also see that my 3 CMCs are all through the ETH2 ports connected to subnetwork 1. Okay, very important, RelaySimTest. You can use RelaySimTest only with the net2. And it's also mentioned here, net2 comms boards on your CMC. So for the guys out there who still has the net1 range, I would advise if you want to use RelaySimTest, please upgrade your CMCs. We have sent numerous communications on this. This is the benefit that you can have if you have the net2 board, and you'll recognize that this is how we've set up our system here with the net2 board as well. Okay, coming now to my full system configuration. Very important why it has to be the net2 board is because of the PTP. Now, the PTP, Precision Time Protocol, is important because that is the way you need to synchronize your 3 CMCs together so that all of them are in synchronicity when we are testing. So all 3 units would operate as if it is 1. To achieve that, you need the Precision Time Protocol. Okay, you'll recognize that all my CMCs are offline. That is for a reason, because I want to show you guys, I'm going to plug in my 1 network cable to the switch, and then it will start picking up these CMCs, and then it will first show me that it's connected, and then on the left-hand side, we will see an icon coming up here, first orange, to show that it's initializing the synchronicity, and then once it's detected and synchronized them together, it will turn green. And once all 3 CMCs are green, it means they're all synchronized to the same time source, and that means I can operate them as if they are 1. And there we go. So now I can see that all 3 CMCs are now synchronized through the PTP. Okay, pretty awesome, right? So once I have my system under test configured, I have my test configuration sorted out to say what current outputs are associated to which inputs on the relay. I'm now at the point where I can start developing my test cases and then also run some tests here. So let's have a look at what our test cases are. So over here, my test manager, this is giving me an overview of all the tests that I've added here. And what I've done here is I've only got about 1, 2, 3, 4, 5 tests today. I've only done 3-phase tests because that's only in the interest of time. If I see today the time is okay, I will just, while we are busy, adding a test here or there with a phase fault or a ground fault, and then we can just use that to simulate that as well. Okay, so let's go quickly to the very first one here. So all these tests are looking at this test configuration over here and this system up here. So let's open up the first test case. Okay, just waiting for it to load. There we go. Okay, so the reason now why we have this is so that we can understand what system we are testing. And we have a lot to digest here, so I'm just gonna try and gradually work through what we're seeing here. And as we go through the other tests, we'll obviously see a lot of these things come up. It will look repetitive, but the testing will be different every time in terms of where we are positioning those faults that we are simulating. Okay, so if we have a look here on the first screen in the middle here, this is the test system that I have previously now configured. So this is my incomer 1, 2, feeder 1, feeder 2, the bus section, and then obviously my IEDs in this system. If I scroll down here, you'll recognize that there is what's supposed to be my transient displays here. So you'll see this completely gray bar here. Actually, that is my transient currents. If I'm going to quickly make this 100 milliseconds, you'll actually start seeing that these are the currents that's being displayed. The only reason why, if I put my 30 seconds, I want it to be 30 seconds. If I simulate this test for 30 seconds, it condenses all of those waveforms into 30 seconds, which this screen is over here. And it's simply just doing that. It's compressing it together so it now looks as just one solid bar. But in reality, these are your currents in the background that are being simulated. Okay. Then if I can just scroll up here back to my system, on the left-hand side here, these are my currents, my analogs, and you simply add them here by just, if you click on the system, you can just add them. If you click there, you have a pin there, so you can pin them to the left or you can unpin them. So obviously I've just pinned all my CTs to the left. And when I'm simulating a system, these are the currents that will be displayed. And you can recognize for this test, which is my through-fault stability test, I have incomer 1 and feeder 1 seeing currents, and they are being separated by 180 degrees as an in and out scenario. Bus section is seeing nothing. And then I'm seeing on feeder, incomer 2 and feeder 2, again, currents coming in and going out with 180 degrees shift just to simulate in and out again. And that is the reason why the bus section is not seeing anything, because it's not distributing any currents through here because there's no fault. So at the moment, it's creating an ideal situation here, ideal simulation of my power system here. Okay, so let's run the test and let's see what it comes back at. At the same time, I'm also going to show you guys on my SEL relay what that looks like when I'm starting this simulation. So let's go. First, I need to apply the configuration. So before we do that, on the right-hand side over here, you can see there, it shows me that my CMCs are all synchronized, but it doesn't show me that the GOOSE has been applied yet. So I need to apply that configuration. And once I've applied that configuration, it will now simulate GOOSE to the 487B. Okay, well, I could easily say it's simulating it to the 487B, but then maybe I'm lying. So let me show you guys that I'm actually simulating it to the 487B. Remember, there's no 451 here. So let me go to my terminal window here and just type in the GOO, and this command on the SEL relay shows me here that this 487E relay is publishing a data set, but it's also receiving a GOOSE, which is over here. Okay, so it's receiving that GOOSE message. Okay, So now let's do something interesting. Remember when we said that if we look at our virtual signals, which was VB001, if I look at that, I see a 1 there, which means incomer 1 isolator is closed. Now, if what I'm saying is true, and I'm simulating the GOOSE configuration, if I were to open this disconnector, then I should see VB001 actually being in the open position. So I'm going to open it, and I'm going to apply this as the new configuration. And let's have a look at what my relay is saying now. So going up, there I can see virtual bit 1 has gone to a 0. Now I can quickly just, for the sake of interest, I can just quickly open up all these disconnectors. And if I do this, then realistically, I should also see all those virtual bits dropping off when I apply the configuration. Also notice here on the left-hand side, right, how this is dynamically updating the current flow as well. So because I've opened all the disconnectors, there's 0 current flowing over here. And if I apply this configuration and I now go back to my relay and I say, okay, let's look at my signals, you'll notice that all those virtual bits are now gone because I'm not simulating the closed status, but I'm actually simulating the open statuses, which is VB11 to 16. Going back to my relay, now pay attention to the left-hand side, how this dynamically updates as I switch in my current, my disconnectors. So incomer 2 closes, and then I'm going to close feeder 2, and then you should see now there's currents, because there's a system that can actually have a closed system with current flow. Similarly, now if I close incomer 1 and feeder 1, current should be applied into that circuit there. And now if I close the bus section, obviously still nothing because I'm not having any faults at the moment. And again, if I apply this configuration, this is what's being simulated to the relay. And now I can see that virtual bits 1 to 6 is simulated again. So this is proof that I'm sending these signals via the GOOSE. It's no other means of getting to the relay than that. So for my through-fault stability, what I would like to do is inject the relay for 30 seconds, and then I can now also at the same time monitor that current flow on my relay to see if I can see all these currents there. So let's say apply configuration. I think we've done that just now, but no harm done in doing it again. And then we can say execute, and then I'm injecting this power system. So if I look over here on my incomer 1, incomer 2, feeder 1, feeder 2, and then my bus section, I should see currents in everything except in the bus section. So I'm just waiting for the system to, yeah, there we go. So now I can see currents are being injected in all the bays except the bus sections. And I can see this is 0 and 0, and then it's got 180 and 180 degrees shift between the incoming side and the feeder side. So what I'm seeing here is accurately representing what I'm simulating from RelaySimTest. And I've simulated all of this by publishing GOOSEs to the relay. The relay subscribes to that, and it knows exactly when which bays are switched in and which ones are not. So you'll see on the top-hand side here, it passes my test because I've said no trips should be received during this simulation because it's a through-fault stability. So there should be no trips associated to this. Okay, so once we've done that, I can now minimize this, go back to my main testing screen. Just bear with me, just quickly want to check something over here. Okay, now I'm happy with that. So now we can do an actual trip or an actual fault. So let's expand the next test case, which is now a test case where I'm going to be simulating all the bays are switched in. Again, I've got incomer 1, incomer 2, feeder 1, feeder 2, and the section closed. And I'm going to simulate a fault on busbar 1. Now recognize how my system looks different in the transient side of the simulation. So here now I can see there's 2 conditions here. There's the pre-fault and there's the actual fault condition. You also recognize that obviously the current flow significantly increases as there's a fault. I'm simulating a 3-phase fault, so all 3-phase currents are adjusted accordingly. If I go down now, I can see that for the pre-fault condition, I'm expecting all of them to come through as stable. But then here, when there's a fault, I'm expecting some current flow to develop in the bus section. And that is because if I have the fault here, I'm also sourcing current from the left of the right-hand side of the system to the fault. Okay, so let's see if I simulate this system, what it does. So I don't need to explain the currents again, I believe. I don't need to explain how I'm switching bays in and out. So let's simulate this condition, and then we see what happens. What I can mention is what I expect to happen here. This being a solid zone 1 or left-hand side or busbar 1 fault, I expect incomer 1 to trip, feeder 1 to trip. I do expect the bus section to trip, but I do not expect incomer 2 and feeder 2 to trip at all. So afterwards, I would expect that to be a stable system. So let's apply our configuration, make sure all the gooses are sent, that all the disconnectors are closed, all the breakers are closed, and then let's run this test. Pay attention to my fault over here as it goes through the sequence of events. So you will notice that for incomer 1, for example, it has dynamically updated as it went through the sequence of the fault. So if I'm scrolling down, you'll see that it's giving me some information here. So let's start. This was a pre-fault condition. So first of all, everything was balanced. Then under the fault condition, the section had currents, and then when the section had its currents, it would trip zone 1 because this is a solid zone 1 fault. Thereafter, I would see that everything switched to zone 1 has been cleared. No current flow in incomer 1, no current flow on feeder 1, and then also obviously no current flow on the bus section. You will recognize and notice on incomer 2 and feeder 2, I have currents as the system has stabilized on that side. And also if you look at here where I click between these different states, it highlights it. Then as I'm clicked here in the final state, you'll notice now that there I've got incomer 1 breaker open, bus section breaker open, and feeder breaker open. This is the case because I'm simulating all these disconnectors and breakers via the GOOSE, so the whole system can at any given time know what has been published, what has been received, and simulate this whole system according to that. Now, look at the pass and fail assessments up here. So I've already configured this to evaluate the system, and I can see that the bus section has tripped. I can see that incomer 1 and feeder 1 has tripped, and feeder 2 and incomer 2 had no trip signals coming through, which means a fault for zone 1 or the left-hand side or busbar 1. It isolated that fault accurately, correctly, and also quite fast. Within 11 milliseconds, it was isolated from the healthy system, and the healthy system maintained current flow. Okay, let's now look at another test case here. The next test case is now if we look at a busbar 2 fault. So let's expand this. Looking at now my busbar 2 fault over here, if I can just scroll up here. So again, this is going to be my whole system at start. Everything is closed, and I can see that. And if I go to the pre-fault condition here, I can see it's a balanced distribution of currents all through the system. I can also see that in the transient system below. I can see again on the section, no currents initially. And then when there's a fault, I expect currents to flow through the bus section as it is sourcing currents to the fault from the left-hand side as well. When I have the fault, what I expect to happen here is a tripping of incomer 2, feeder 2, and the bus section, and then isolating the healthy side to the left-hand side, and I'm not expecting any trips there as well. So let's see if that is what I'm getting. We can apply our configuration, make sure the GOOSE is configuring all the systems switched in, and then we can say execute. And again, we can now update. I'm scrolling down. So we can compare incomer 1 and incomer 2 on the transient side to see how they compare to each other in terms of the system behavior. Okay, so interestingly enough, we had a different operation than what we would have expected, and that is because of the coupler security logic. And I'll explain that now. So what we have in our results is that bus section has tripped, and incomer 2 and feeder 2 has also tripped. You'll recognize that it's a slightly delayed trip time, and the reason for that is because of the zone 2 being part of this CT circuit here. Obviously, this would be a solid zone 2 fault, but because I don't have a second CT here to make sure that that fault is not here, what I'm doing here is implementing the coupler security. And remember, I explained this to say, I will have to make a decision. If I'm configuring my system to take speed as priority, I will trip zone 2. It will trip immediately all the zones to make sure that it's isolating this fault. Then you have speed. But if I want to have selectivity and isolate zone 2 accurately and not trip zone 1 for a fault in zone 2, then what I would need to do is apply the coupler security. Now, that is only done if you can live with a short delay on your operation. In an HV system, most probably not, but in an MV system, you can live with that time if selectivity is more important. So let's see if my relay behaves properly. So the fault being here, the very first thing I do is I take out the bus section to make sure the bus section is out. Once the bus section is taken out, that means if I go here, just want to scroll down, go to this part here. Now we can see the bus section has been opened first. We know that it's opened or tripped in 10 milliseconds. So once this is out, this CT here is taken out of any differential calculation. Now the relay will reevaluate and reassess the whole system and see what is balanced and what is not. So at that instance, it will recognize that now, and that is why current flow is here in incomer 1 and feeder 1, because now it recognizes that this is still balanced, but if I go down here, incomer 2 and feeder 2 is not. And then it makes a new decision to say, okay, this definitely is a zone 2 fault, so I can then isolate zone 2 accurately. And if I scroll down, you can see that zone 2 has been completely removed without affecting zone 1. And if I click on the fault here, this state here, you now see that incomer 2 and feeder 2 and the section has been removed. So this proves to me that my coupler security logic is working, and I'm happy with that, and the result looks good. Okay, let's look at another test case now, and now we can look at when I have a busbar fault with the bus section in the open position. So let's open our test case here. Okay. Okay, so now let's have a look at this system that we have here. Again, I'm simulating now the system, I'm simulating this system with the bus section in the open position, and I'm putting that fault between the CT and the breaker. So what am I expecting when I'm having this fault over here? So obviously when the breaker is open, due to coupler security logic, it's removing this CT from any calculations in any regard, which means in this scenario, busbar 1 or the left-hand side should be unstable during the fault, but busbar 2 should be stable because there's a separation there, so no current flow to the fault. We will expect to see that in our transient system as well as in our conditions here. So let's apply our configuration, and then we can execute the test and see if what we are getting back is accurately represented. So don't be alarmed about the characteristics here, seeing these sine waves being small and large. If you look on the left-hand side, the scaling is slightly different. This is in milliamps and in amps. So in reality, these are actually very close to each other. It just looks different because this scale has to accommodate the fact that it's seeing the fault current. But what we can see from the system is that incomer 2 and feeder 2 had no fault condition, no effects to it, no tripping, no elimination of any currents, whereas between incomer 1 and feeder 1, we actually had that current flow and it spiked. And obviously we are simulating onto that CT, because remember now, even though this breaker is open, that CT will still see current, but my relay will ignore it. And that's what I'm doing here by injecting on that CT on the bus section as well, is just to have it there so that I can prove that the relay is ignoring it. And we can see that it has done so because bus section didn't trip. Obviously it's open. Incomer 1 and feeder 1 correctly tripped. If I go to the fault state here, there you can see incomer 1, feeder 1 is tripped, it's open, and incomer 2 and feeder 2 has correctly stayed in place. And obviously I can see my system stayed throughout the whole simulation, stable with no effects to it. I can also, if similarly, just look at the digital signals here. I forgot to mention that earlier on, but you can look at your GOOSE signals as they are being received and as they are being transmitted and simulated through the system as well, similarly as to how I can see them actually live here on my power system. So seeing that these disconnectors are open and closed, it's more visually interpreted here. You can visually see here, obviously, if I go to the fault, this is tripped, so you can see that. But you can also monitor those conditions. If you scroll down, you can see here that incomer 1 received a trip and feeder 1 received a trip. And you can also see that none of the other bays received any trip conditions via the GOOSE. Okay, we can now minimize this and go to our next test case, and we can just expand this one. So this is a little bit of a more interesting one. This is now where I have the fault between the breaker and the CT. And obviously, this is actually quite similar to the test that we've previously done in zone 2, where if you have a fault in this region here between these CTs, whether this breaker is open or closed, there's absolutely no ways for this system to know where on this bus bar will this fault be. So this simulation is just very similar to the previous one, but this is just proving that when I put the current between the breaker and the CT, it will correctly, again, just aside from the fact that I could have placed it here, but when I place it between the breaker and the CT, it will correctly apply the coupler security logic, delay the tripping of zone 1, and then it will correctly take out the section with an accelerated trip, reassess the whole system. In that case now, zone 2 will be stable, but zone 1 is the one that should trip. Now, this is where it becomes different from the previous test. Remember, it's very similar, but in the previous one, the fault was here. So if you open the breaker, we had zone 2 trip. If I have the breaker open here now, I should see that incomer 1 and feeder 1 should be the ones that's tripping, because this is where the unstable system should come from and not zone 2. So let's simulate this and see if this is what my system is, or my RelaySimTest is getting back from the system, and that it agrees. Let's execute the test. So we should see an accelerated trip on this section. Let's hope this works exactly as we explained it to be. See, I've got a couple of things I want to. Okay, so let's evaluate and assess what we are seeing here. So in the first instance, I had all the bays seeing normal current flow. Again, don't pay too much attention to the size of the currents. It's just distributing it according to the scale. But then we can see when I have the actual fault condition, so the section trip. This also agrees with my accelerated trip, so the section opened first. Now, if I go to the next part, here I can now see that even though this is regarded as a zone 2 fault because of the polarity of my CTs towards the object, it correctly taken out zone 1. This is essentially the idea behind the selectivity part of the coupler security versus the speed part. And this is just to say, if you can live with that short delay, you can correctly take out the right faulted zone and not take out the healthy zone as it's here. And if you scroll down here again, we can see that I just want to find feeder 2 here, and there we go. So I can see that after the fault has been cleared, feeder 2 and incomer 2 has correctly stabilized as it was unaffected by this whole system. And then your system continues after that. And the tripping conditions agrees with what we expect to see. Okay, so obviously this actually pretty much wraps up what I wanted to do. Just since I see we have a little bit more time before I'm going to head into questions, is let's see if we simulate now a ground fault, what the behavior would be of the system. So I'm simply just going to take exactly this same test. I'm just going to duplicate that, and I'm going to, you can maybe just call this now ground fault. Sorry, caps there, ground fault. And now we can just open up. Now also, obviously what we are testing here is relay logic, and that is the emphasis of RelaySimTest and the power behind it to test this relay logic. Now, you would remember from the presentation side, at one point I mentioned one of the benefits being the iterative closed loop function, and you'd recognize in all of my tests the iterative closed loop function is highlighted. And the reason why that is such a huge benefit is because what it does is if you enable the iterative closed loop the first time around, you run any of these tests, it kind of learns the behavior of the relay's outputs to RelaySimTest. And then the next time around, when you want to test that, it already knows what it was expecting to see. So I'm using that because it learns the logic from the relay and then it adapts the test to that, so that when you simulate that test again and it sees different signals, it will actually give you an error message here saying, I've received different commands or signal as what I was previously expecting based on what I've learned. Now, there's a lot that we can add or discuss to the iterative closed loop. It's going to take us a lot of time to go through all of that. So for the interest of time, I'm not going to spend a lot of that, but I want you guys to understand that it's kind of like an adaptive system where it learns the behavior and the algorithm and the logic of the relay, but it's also adaptive in the dynamicness of the faults and where you can plot these faults and how you can simulate these faults. So what I want to do now is I want to take exactly this same fault, and what I want to do now is I want to change this just to a line 1 to ground, and then I want to see what that is going to do. So you'll recognize over here, obviously now only the red phase, as it's a line 1 to neutral, has now distorted significantly compared to the other currents. So that's all I needed to do is switch my fault condition from 3-phase to line to ground, and I would expect the system to respond and behave exactly the same way as it did previously. So I can apply the configuration, and then I can just simply say, execute the test, and let's see what happens, and if it simulates that line to neutral fault phase. So from the previous test, we know we want to have incomer 1 and feeder 1 completely isolated, and incomer 2 and feeder 2 continue to run into the system. And there we have our tripping there. It's bisection, incomer 1, feeder 1, and then incomer 2 and feeder 2, no trips at all. And if I wanted to, I could go back and I could duplicate this test again, and I can say, now I want to simulate line 2 to 3 or line 1 to 3. And so I can create more and more test cases, all based on the same configuration. Another thing to also mention is here, if you look on the right-hand side here I've got a comment section. So I have, for each of these tests that I've simulated today, I've added a brief description of what I'm expecting to happen even before I'm testing. So if you want to reuse this test template and another engineer or test technician is using this immediately, but just referencing the comments in here, you can have a broader understanding of what is expected to happen and simulate the test and run the tests. Also, what I also want to mention here today is that, yes, we have made this very nice. We've set up with 3 CMCs, and that's it's a unique setup, and you probably most often won't actually have that many CMCs available to play with the system, especially considering when you have an 18-bay buzz-on scheme, you obviously won't have enough CMCs to run that unless you bring in about maybe 12 CMCs and start testing that. But the point here is yes, I had these CMCs available. I could use them, and I have, but you could also do a lot of these tests with only 2 or 3 CMCs. Or just even 1 if you want to do single-phase testing. It's still possible to adapt the test template to be utilized to that extent. And that is the benefit of RelaySimTest, is its adaptability to whether you want to test with 1 or 2 CMCs, 3 or 4, or in some cases where we previously done this on an ABB scheme, we tested the 18-bay buzz-on scheme by using only 4 CMCs. No, correctly, initially it was 6 CMCs. So we used the 6 CMCs to simulate a lot of the bays at the same time. And then we actually moved over to 2 CMCs only, where we had 1 CMC simulating 2 bays and another CMC simulating the 2 CTs on a section and a couple at a time. So the point is that you don't need that many CMCs. If you have them available, great, awesome. It's pretty fun, believe me, from doing this now a couple of times. It's really fun to play with it like this. But if you don't have that many CMCs, it's not the end of the world. You can still configure your system configuration here on the left-hand side, the tested configuration, to be using only 2 CMCs, and you can still achieve the same results at the end of the day. So now that we've run all our tests, the last thing that we would need to do is go to report, and from here we can now just say export the report to Word, and then you have all these tests with the power system and everything configured into one document. You can print this to PDF, and you can email it or send it to whoever needs it, to the relevant supervisors or managers to make a final decision, and then commission the system if you have to. Just want to show you guys what that looks like. There we go. So this is what your test system would look like. So we had 6 tests passed, 0 failed, and then it details each and every test with the simulation and the power system, where the faults were simulated at, and the results for those tests. Pretty neat if you ask me. Okay, guys, so that is the practical side. So what we can do now is going to stop the screen share, and then we can now maybe look at some of the questions if you guys have any questions. I'm just opening my chat block here, so let's have a look at here. I have Pietri van Wyk, can RelaySimTest produce its own independent CID instead of simulating another relay? No, unfortunately not at the moment. You still need that, that dummy CID or the dummy relay that you need to simulate, because RelaySimTest takes that dummy relay and just basically create it into RelaySimTest and simulate it as if that IED exists. You can't create a CID in RelaySimTest to simulate that. So no, it can't do that at the moment. Then Musa, morning Riaan, for single bus section CT with regard to blind spot fault between bus section CT and bus section breaker, how is selectivity actually achieved against speed in consideration to a fact that as long as the bus section breaker is closed, right-hand side bus bar fault cannot be easily differentiated from the blind spot fault. An example, right-hand side bus bar fault will always be cleared only after tripping the bus section. Yes, this is actually, I think I've mentioned this, I've covered that. That is one of these tests that we did. So this is this guy here. Okay, so let's just clear the results over here. Okay, so if we look at the system, this is exactly what Musa is explaining. If the fault is between the CT and the breaker, this is regarded as a dead zone or a gray zone. There's many terminologies to it. At the end of the day, the reason why this is a problem is because, as Musa has explained, you can only accurately define where that fault is once you've opened the breaker, and that is exactly what we are doing. The relay logic has been configured with the coupler security, which SCL has a very detailed logic for. It's very good, it's very accurate, as you can see, it works very nicely. So what that logic does is when the bus section breaker is closed, it actually implements a zone blocking logic. And that zone blocking then is applied to the bays except the section. So when there is a fault, it will block all the bays, but it will trip the section first. That is why when we run this test, you always see the section has a faster trip time in comparison to the other bays. So it trips the section first, and then once the section is tripped, it reevaluates the system to see now where is the distortion. Is it on the left-hand side or the right-hand side? And then it makes a new decision and then accurately takes out the respective bays. In other words, it recalculates the differential currents based on where that fault is. So now you can see bus section tripped in 10 milliseconds. If I go to the fault, section has been removed. The fault is still there. The CT is still being injected. However, my relay would now completely ignore that current because now it's out of the differential equation. And now the SCL relay will reevaluate the differential currents. And now it will see there's no distortion happening on incomer 2 and feeder 2. But there's still something wrong in incomer 1 and feeder 1 side of the bus bar. And then if you get to the fault, it accurately tripped incomer 1 and incomer 2. This is a zone 2 fault in principle because it's within the CT zone of zone 2 or bus bar or the right-hand side bus bar. But because of the coupler security, we can properly differentiate between where the fault is. Musa, I hope that answers your question. Then I have a comment here. Riaan, very awesome presentation on this feature in the software. Very well presented. Thank you, Dion. Really appreciate the support from you guys. You really have made this possible for us. So thank you so much. Yasin, thanks, sir, for your presentation. It was very helpful. And then Quibus, thanks, Riaan, very informative and relevant. Okay. Andre, do you have any other questions on your side?
No, I don't have any other questions on my side.
Okay, so guys, thank you again for attending today's session. Okay, Musa's got another question here. Sorry, is there a limitation of how many CMCs can be connected to RelaySimTest? Actually, Musa, I don't know. We have run 6 in the past. I believe you can do more. What the limitation exactly is, I don't know. I can maybe read up. I don't think the brochure actually also even mentioned that. But I honestly can't give you an answer on that. I can tell you that it's more than 6. We can probably go up to 10, but the exact number I'll need to confirm and get back to you on that one. Okay. Okay, it doesn't look like we have anything else. I do remember a comment on our LinkedIn post that we had, and I do want to address that. I kind of alerted to that in the presentation, that at the end of the day, what we wanted to simulate here is not a substitute necessarily for the hardwire configuration. I mean, by all means, if that is something you can do it. If you have a reliable 6150 network and your specifications are calling for that you have a 6150 buzzer where all your signals are 6150, great. This is another way of testing that. If you don't have that whole board available to simulate it, you can exactly still use this. But what we wanted to emphasize here today is that if you have a hardwire buzzer, you can just, if you have time on the onset to actually configure that virtual test signals in parallel, you can simplify testing so much. If you just think about how many signals you would need to wire on the binary inputs and outputs just to simulate that whole system. Even for this small, simple system we have here, you would need to wire in all the open and closed status for the disconnectors, the breakers, and you have to wire all the tripping contacts. And then if you test that, it's a lot of wiring to test on. So the idea, the concept here is to actually just show you guys, if you have 6150 available on your IEDs, just have a test configuration, apply that in parallel, which means it will still work. The output from the hardwire or the output from the virtual signal goes through an OR gate. So whether you test the hardwire, whether you test the virtual signal, the functionality is still proven beyond a doubt. And if you have at FAT stage properly tested those inputs, the hardwire solution, you would know if you've tested on the virtual solution, it will work just the same. So we are not saying it's a substitute. You can have hardwire signals, or in some cases, if you want to go fully 6150, great, do it, awesome. So from my side, I don't see any other questions. Andre, I assume there's no other questions on that side either. So thank you guys so much for attending, and thanks to SEL again. The guys have been very helpful. Skippy, you as well, Rudolph. The guys have been really helpful to get this working, and also to Theo and Pietri for the support on the CMCs. Thank you guys, appreciate it. I enjoyed it. It was fun. It was really, really fun to do this. And I hope to do another session like this in the future. So if there's nothing else from your side, guys, have a good weekend. Thank you for attending. I'll see you guys soon.
Okay, great. Yeah, thank you, Riaan. Of course, yeah, thank you everyone for joining us this morning and spending the time with us. Of course, if you have questions, you can always send them to us and we can get back to you on those. And then just regarding, just a reminder that this webinar will be sent to you later today. So just keep an eye out for that. And then, yeah, we look forward to seeing you on the next one. And just a reminder, next week we won't be having one because of the long weekend. So just keep in mind. But yeah, we look forward to seeing you on the next one. So have a good weekend and stay safe and keep well. Thanks. Goodbye.